right to it. We're going to do the following things. Obviously, we're a little behind. What we're going to do is this. I'm going to talk about substitution today, and I'm going to do a video for area between curves. Area between curves is probably fairly comfortable for you, and so it'll be kind of like a refresher video more than anything else. And we're going to focus on substitution. Before we get going, I would like for you to answer the following question in your own mind. With regard to substitution, I can do all the homework. I can do substitution with some help finding U's, or I'm lost.
What if you're in between two?
Yeah. In between the top and
I can do 99% of them. I can do all.
Yeah.
There was one problem I couldn't find the U, and then as soon as I found like I would have never seen that, but it makes complete sense.
And then there was one.
I'm a little
three
lower, but
on the first one,
Like, I
and
can
one
do
on the
this.
second homework that I
Yeah.
like 23.
Okay, so that's an okay place to be. Sometimes with the U substitution, you're like, what? I couldn't have seen that, but now that I've seen it, I'll remember it. Kind of a thing. And that's totally cool.
Thinking to make ln sine x as a U, so that it goes 1 over, and then you have the cosine on top to get the cotangent.
Oh, you did last night's homework.
Yeah.
We're not supposed to.
Oh, see, today, what I talk about today is going to satisfy that.
Oh.
But even the day before, I had a problem.
Yeah, even the day before, there was like only like one or two. One of them was like they gave me a U, and I was like, I can't see that at all. And then
It
the
gave
other
me a
one,
U and it didn't work, and I was like,
and I was
Yeah,
like,
I think that's
what?
fine.
Which one is that?
I think it still worked. I mean, I just couldn't.
I think
I'm
it
assuming
worked
it does.
eventually, but I was not
Okay.
fine.
Is there anybody in the lost category? Okay, good. All right, then let's immediately address the one where they gave you a U and it didn't work. Because that
or it at least didn't seem to work.
I just couldn't get
All the
it.
ones they gave me the U, I got. I'm pretty sure it is.
No.
Is it perchance number 21?
Yes, that's the one.
Yeah, that's the one. Then let's immediately talk about that because yesterday's lecture was supposed to be about this.
This is a quick sidebar question, but it can be answered quickly. When it's ln to the 6x, does that mean ln to the x whole thing's to the 6th power?
Yes,
Okay.
exactly. It's analogous to the trig functions. All right, so I want to talk now about the antiderivatives of trig functions and the antiderivatives that result in inverse trig functions. Notice I didn't say antiderivatives of inverse trig functions. We'll do that with parts.
Yeah, but I want to use my paper just like this. I was like,
And
I
the
can't do
reason
this.
that we want to do the antiderivatives of trig functions as a kind of separate chart is twofold. One is it gives us some insight as to how to choose U's, and number two, we need to know how to anti-differentiate these things. So it's partly factual knowledge. These two are automatic. These are elementary functions. So this one's going to be negative cosine x plus c, and this one's going to be sine x plus c. The negative sign on the cosine here is commonly forgotten, so I have as a rule for myself, even after 30 years of doing calculus, take the derivative in your head. Just make sure you don't look at the negative signs. Okay? So there's that. With tangent and cotangent, we're going to use substitution by rewriting as sine over cosine, and then letting u equal the entire denominator, which is cosine x. And if u is the entire denominator, then du is negative sine x dx, so that just a little bit of repair will take care of the issue for us. So that we now have negative integral of du over u, which is, of course, this guy right there. This is a perfectly good answer. No self-respecting mathematician writes it like this because The derivative of tangent is secant squared. Therefore, to keep it all in the family, we're going to use the log properties to rewrite this as an exponent. And 1 over cosine x
Apparently I'm not a self-respecting.
Yeah. Google
It's-
also was not a silver person.
It's also-
When I found this question.
is secant x.
I looked at this and like it works. But
I know.
it's magic.
I looked straight down at the answer. I was like, that doesn't make sense. I scrolled up. I was like,
Yeah. No, we do this in order to keep a kind of symmetry between derivative and integral. With that in mind, what I'd like for all of you to do is in about 30 or 45 seconds, show that the integral of cotangent x is negative natural log of cosecant x plus c. Go. What slightly clever trick shows up halfway through?
Concerned because I don't know what clever trick it was, but I thought I got the right answer.
You did. How would we get from here to here?
When it's still a in the integral form, do you do the repair of the negative sign even though you don't need it?
Even though.
Oh, yeah, you sure could. How would that look?
sorry.
Then you would have negative ln sine to the negative.
Mm-hmm.
So then you'd have negative,
Basically.
and then you can pull it like you did last. Just make it equal log properties.
Yep, that's exactly it. So what we did here was a theme that we've seen this year, which is that we artificially introduced a double negative in order to make it work. It's like adding 0. It's like multiplying by 1. That's exactly right. And self-respecting mathematicians have that in their toolbox. As this is a thing that I could do. If you did not see to do that, if you did not see to do that, the way that self-respecting mathematicians look brilliant is they take what they're supposed to show and they work backwards. Because if I write this as negative natural log of 1 over sine, then I immediately see that I can pull off the double negative right here. So this is what I call the bridge method. You start with the left-hand side and you get to the right. But if you can't get all the way there, you get halfway there, you start with the left side and work backwards, and then you reverse the steps, and now you're there. Okay? So that's a basic mathematical thought process. All right. Now, the integral of secant and cosecant requires special care in feeding. Because we are going to pull off a U substitution, but to do that, we're going to pre-treat it with a little bit of algebra. And the algebra is not obvious. You have to file this in the I need to remember this trick thing. And so I'm just going to show it to you. What we're going to do is to multiply by 1. Specifically, we're going to multiply by secant x plus tangent x over secant x plus tangent x. And you say to yourself, I never would have thought of that in a million years, and neither would I. But somebody did, by dorking around either with derivatives or antiderivatives, and here we are. And you say, how did that help us? The reason for this is not obvious until we simplify the fraction that we have. And now we have hit pay dirt, because if we let u equal the entire denominator, then du, which we know automatically to compute, is going to be secant tangent, secant x tangent x, plus secant squared x dx. Would you look at that? It's right there in the numerator. Mathematically. This is one of the most interesting arbitrary things that happens all year. So that we have then du over u, which gives us the natural log of the absolute value of secant x plus tangent x plus c. This is one of those results that you want to replicate for yourself a couple of times so that you can see how the logic works so that you don't forget it.
Is there some reason that there's a correlation between all the antiderivative of some trig functions and natural log? Is there some correlation there?
At a deep level, yes, and it relates to your other thing that you're interested in, which is e to the I equals -1.
So we will get to that later. Is that later past?
Kind of. We will get to the relationship. Yeah. I'm not sure we'll answer that specific question. Does this make sense, everybody? So far. Okay. The integral of cosecant is going to be very similar. Walk me through it.
So multiply by 1.
Mm-hmm. What kind of one?
Cosecant plus cotangent.
Let's try it.
Yeah.
All right, keep going.
Cosecant squared
Cosecant
plus-
squared
yeah.
plus cosecant x cotangent x all over cosecant squared plus
Cosecant x plus cotangent.
Yep. Okay, keep going.
denominator is u and top will equal d.
Don't rush it. Denominator is u. du is?
Negative.
It's negative.
Okay. So now what's needed?
You need a negative.
We need a -1. That's right. So we're going to
Multiply by -1 and then repair it.
Repair.
repair. We're going to use repair. Okay. And this gives us now negative ln cosecant x plus cotangent x. And this also you should do a couple of times for yourself so that you can see the logic in it and you don't forget it. However, there is a strange algebraic thing that can happen with this. This -1 right here can be used as an exponent, right? Because of log properties. So let's explore what happens when we do that. Now, at first, this doesn't seem like we've done anything. But now what I'm going to do is to rewrite in terms of sines and cosines. This gives me ln of like so. And now I arrive at the second possible way of expressing the antiderivative of cosecant, which is sort of unusual. But wait, there's more. I can multiply top and bottom by 1 minus cosine x to rationalize. And when I do, then in the bottom, I get 1 minus cosine squared, which is also sine squared x. These cancel, and I get 1 minus cosine x over sine x. This is one of the more involved algebraically results we've had all year, because now the final thing, this is the same as 1 over sine x, which is cosecant. And this is the same as cosine over sine, which is cotangent. So the very odd thing that we get is two different results involving cosecant cotangent. We have negative natural log of cosecant plus cotangent, which just happens to be equal to the log of cosecant minus cotangent. It looks like I brought the negative 1 to the inside in a weird, strange way, but actually what I did was a lot of algebra. So one of the things that you can do for yourself sitting board in English class is to say, self-prove that the integral of cosecant is equal to log cosecant minus cotangent. And that'll keep you occupied for at least 20 minutes.
Yeah, right?
Yeah. Okay? Good? Eric, good? Okay. Not good? All right. Well, let's do a new topic, and that new topic is going to be the integrals that involve inverse trig functions.
Is lunch enough?
Yeah.
Oh, I had to use that one.
Today is a good day.
I had to learn it.
And these three are going to be new antiderivative rules for us. They're going to be forms involving 1 over root a squared minus x squared, 1 over a squared plus x squared, and 1 over x root x squared minus a squared. Yes,
Why can't you just use the inverse trig function?
that's exactly what we're going to do. Yep.
We're just gonna make it easier.
But all three of these are going to require a specific substitution to make it work out. So what we're going to do is, in all three cases, we're going to let u equal x over a. Or in other words, we're going to let x equal a times u. Now, first, this is not obvious, but as soon as I pull off the substitution, you're going to see the brilliance of this. You're going to see the logic of it. So here we go. If x is equal to a times u, then dx is equal to a times du, right? And so now I'm going to substitute. I'm going to substitute into this first form and see how it goes. And I'm going to substitute everything in sight in terms of u. So that we now have 1 over root a squared minus, here we go, au squared times a du. There's the calculus part. Now comes the beauteous part, because au squared is a squared u squared, and when I factor out the square root of a squared, I get a. Everybody check the algebra on that. The key point, the key move, the reason we pulled off that substitution is that the factor of a squared, really inside the radical, is a common factor that can now be pulled out.
Oh.
You see it? That's the logic of it. And as an added bonus, these cancel. So that now I have the integral of 1 over root 1 minus u squared, which is exactly arcsine of u. And since u is x over a, we're done. And that's it. Now, we want to go in two directions. One is the check. The check gets slightly hairy because I don't exactly recapitulate the original, right? I get 1 over root 1 minus x over a squared times the derivative of the inside. And to see that this is equivalent to the other, I need a little bit of common denominator action. The denominator here is a squared, and so I get a squared minus x squared, all of that over a squared, times 1 over a. And so now we end up with this compound fraction, right? And this gives me, let's see, it's 1 over the square root of a squared minus x squared, all of that over a, times 1 over a. And you can see that here in the denominator, the a and the 1 over a cancel. What's that?
I thought it was over a squared.
It is, but it's the square root of. And the square root of a squared, for positive a, is going to be a. Why is it always, by the way, positive a? Well, it's because the integral presents itself in terms of a squared. And so I can choose whether I want the plus a or the minus a, and of course I want the plus. The second thing is how this works out in terms of antiderivatives, in terms of definite integrals. So let's take a look at that also. Suppose I wish to integrate 0 to 1 root, let's say, 4 minus x squared dx, something like this. I think that'll work. Yep. And so we pull off u equals x over, careful, what's my a? 2, not 4. Everybody falls for that at least once. A squared is 4. So a is 2. And so I have to compute like so. And so we just remember that we're going to need to redo the limits of integration just like that. Why does the 4 disappear? I went too fast. Let's see it disappear in slow motion. So we have 4 minus. Now x is going to be equal to 2u. And dx is equal to 2 du. And so I pull out the factor of square root of 4. And so I get arc sine of 1/2 minus arc sine of 0. If you know the form, however, then you can cut straight to the chase. Right? This is going to be pi over 6 minus 0. Special angles. Let's see the arctangent happen. Because we end up with a slightly different result. We're going to pull off the same substitution. We're going to let u equal x over a, or in other words, x equals au, and dx equals a du. By about the 5th time that you've written this, you'll be able to do it in your head. But I want to encourage you to write it out a couple of times so that it's cemented in place. And so when I pull off the substitution, I get this guy right here. And again, I have a common factor of a squared, but this time there's no square root involved. And I also have a factor of a in the top here. so that one factor of a cancels, but not both of them. And that's the difference that we have for the arctangent form. Just like that. So the factor of 1 over a is sitting there on the outside because we had two factors of a in the denominator and only one in the numerator, unlike the arc sine. There's no square root. Let's see if I can do arcsecant in 2 minutes. U equals, everybody? U equals?
X over A.
X over A. So that X equals a U, dx equals a du. And we pull off the same substitution here. Notice I have an AU right there. And I also have a squared u squared minus a squared under the square root times a du. Now, for this one, we also have two factors in the denominator, but for a different reason. We have the square root of a squared times another factor of a. In the numerator, we have one factor of a. Now, a slightly strange thing appears, and that is that our du's could either be positive or negative, right? However, the derivative of arcsecant is 1 over absolute value of x, root x squared minus 1. And we remember that that was so that the sign of our derivative was always positive. Arcsecant looks like so. Its derivative is always positive. But now, I have something whose derivative could conceivably be negative. So how do I deal with that? I'm going to deal with that by taking the absolute value of here. And the arcsecant of the absolute value of u looks like this, like so, so that when u is positive, I get a positive value. When u is negative, I get a negative derivative, just like that.
How come when you pulled the a square out of the, why did it become, instead of u squared minus 1, it became 1 minus u?
Because I was in a hurry and being silly. Thank you.
And pondering that, trying to figure out how you did that.
Good. I'm glad you did that. And so when the dust settles, what I get is arcsecant of the absolute value of x over a. The bell is going to ring here, so I want to just summarize our three results for these. These forms need to be committed to memory, but the best way to commit them to memory is to derive them for yourself. And when we do trig substitution in the future, then we'll have a second way to get these things.
So there's a homework a day behind, or how are we handling this?
You should be able to catch up tonight. I'm going to do a video on area between curves, and it's not hard.
Oh. Cool.
Okay, so summary. Our three forms. How many of them do you remember? What do we get here?
Arc sine
Sine
of x over c.
of x
Or x over a
plus c. Very good. The integral of 1 over a squared plus x squared dx.
1 over a arctan x squared plus c.
Plus c.
Yeah, you read for plus c. Plus c. 1 over
1 over a. Arcsecant.
Oh, that's
Almost.
ew.
No. X over a is right.
Absolute value.
Absolute value. X over a. Each one has its own little idiosyncrasy. No factor of 1 over a for the arcsine. Absolute value for the arcsecant. And there it is. So I sort of think the arctangent result is the basic one. Also because it involves no square roots, it's the easiest one to derive. So as you're deriving these for yourself so that you don't forget, start with the arctangent. It's the easiest one. And then move to the arcsine and then the arcsecant. Okay? A lot of material. Had hoped to do it in 45 minutes yesterday. We get to do it in 20